Hello there everybody, I hope you guys are doing well. Today we are going to talk about RC circuits, and RC stands for resistor capacitor circuits, and these circuits exist everywhere. The reason we need a resistor to be connected in series with a capacitor is just because the capacitor has a big thirst for charges. So if you actually connect a battery, like here a voltage source, directly to a capacitor, once the capacitor feels that it is connected to a voltage source or a charge source, it's going to draw a huge current. So if I say here it's going to draw a huge current of circuits of charges going this direction, and this huge current is going to maybe is going to be so big that it's going to burn the wire, or it's going to ruin the battery itself. The capacitor will be charged very quickly, and that might not be a good idea as well. So we don't want to connect a battery directly to the voltage. One more note, this is the battery or the voltage. We know the battery is known as the electromotive force, and many books and many scholars would like to use the letter E like this to represent the electromotive force. So from now on we're going to try to represent it also as this way. Okay, now how should you connect a capacitor? You should connect a capacitor just in series with a resistor before you connect it to the battery, and this the resistor will act as an impedance electrical instrument within the circuit to impede the draw of a huge current from the capacitor across the circuit. So once you close this switch, the current would start flowing, all right, and the capacitor would start trying to demand as much current as possible, but it can't. The reason is because of the resistor is going to impede that current. But as the capacitor starts accumulating charges, also the current that is flowing inside the circuit will slow down because it has its charges, and the capacitor does not need any more charges already. So if we draw a graph between the amount of charges Q of T at the capacitor, this is the amount of charges is measured in coulomb across time with seconds. So if we draw a graph between the amount of charges on the capacitor as time elapses, once we here, that's when we close the circuit. So once we close the circuit, what we have on as charges on the capacitor basically is zero, and that makes sense. So at zero time, zero charges on the capacitor, but the capacitor is empty, does not have any charges at all in it. So what's going to happen, it's going to demand a lot of charges because of its thirst for charges. So the amount of charges at the onset of closing the circuit is going to grow quite rapidly. As the charge starts to accumulate on the capacitor, this starts to slow down little by little, and after a little bit of time it plateaus, and there is no more charges flowing into the capacitor. But this means that the capacitor has a saturation of charges, or has what we call maximum charge. So that's maximum charge, and maximum charge they call it also Q0. All right, so that's maximum charge. So now the amount at which the capacitor gets those charges depends on the capacitor itself, the capacitance of the capacitor, and also depends on R. If R is small, then, and the capacitance is big, then this curve will look probably something like this. Okay. If the R is big and the capacitor is small, it's going to look something like this, maybe, or something like that. Okay. So this is like a typical curve of charging a capacitor. All right. Now, for this equation, if we mathematically try to derive it, we have to use Kirchhoff's second rule by implying this, just like we learned in a closed loop, the voltage drops. From there, we can find an equation, and from there, we can use calculus to derive the equation, but we're not going to derive the equation here through calculus. So we're going to get the result, which is the charge on the capacitor as we are charging it during a certain time or through time as a function of time is equal to the maximum charge the capacitor can take times 1 minus e, that's the exponential, to the power minus t over RC. Now what is that? Q0 is the maximum charge. Q of t is the charge at any time of the capacitor. Now this t and this t is the same. Right, anytime. Now the quantity RC, as you can see, if you multiply R times C, this is known in RC circuits as tau. Tau, that is an important concept. Tau is known as the time constant for this RC circuit, time constant of RC circuit. All right. So the time constant of RC circuit, it's called time constant. It's multiplication of R times C. If you get the units of R, which is ohm, and you dismantle that, whatever voltage over current, and you dismantle those, and then you get the unit of C, which is farad, and dismantle that, whatever that takes you to, and you multiply the units of C by the unit of R, you will end up by the unit of tau. What do you think it is? Since it's a time constant, you will end up with a second. So it's actually measured in seconds. All right. So the most important thing here we need to learn is RC, which is known as the tau or time constant. So I'm going to put this in a box here. All right. Now let's test this equation and see what's happening. All right. From there, let's find what the charge on the capacitor. Let's see what the charge on the capacitor here at t equals 0. At t equals 0, this means that we just close the circuit. So how much charge do you expect to be on the capacitor when we just close the circuit at t equals 0? Nothing happened. We expect the charge on the capacitor to be 0. Let's see if this equation gives us the right result. So at Q, at the capacitor, the charge on the capacitor at t equals 0 is equal to Q0, 1 minus, I'm just applying this equation, which we should box to because it's important. Okay. Q, 1 minus E, minus time is 0, remember, divided by RC. All right. Now this equation becomes Q0, 1 minus e to minus 0 over any number is 0, so e to the 0, and minus sign goes away. All right, e to the 0 is 1, so this whole thing is 1. 1 minus 1 is 0, so Q0 times 1 is what? 0. So the amount of charge on the capacitor here, on the capacitor plates, at t equals 0 is 0, and that makes sense. So this means that it is 0, and that makes sense, because there is no charge on the capacitor yet. Okay, let's test the equation on the other extreme limit, which is what? What is the charge on the capacitor after we close the switch for a long time? What is a long time? Now, we don't know what a long time is. It depends on the capacitor, capacitance, and the resistor. So just to be safe, let's assume long time is infinity. So Q at t equals infinity. Okay, let's apply this equation again. That's Q0, 1 minus e to minus infinity divided by RC. Okay, and if we want to simplify this equation, 1 minus 1 over e to the infinity divided by RC, because minus in the power means reciprocal, 1 over, right? So this is can be written again, Q0, 1 minus 1 over e. The exponential function is a very fast function. It grows very dramatically quickly. So e to infinity is definitely what? Infinity. It's a huge number. 1 over infinity is 0. 1 minus 0 is 1 times Q0. That's what? Q0. And that is correct. That is what we are expecting. After a very, very long time, the charge on the capacitor is what? Q0. So actually, that is correct. This equation, again, fulfills the behavior of charging a capacitor in an RC circuit. All right. Let's look at this equation again. I'm going to write it again here. Q of t is equal to Q0, 1 minus e to minus t over RC, because we can actually look into other forms of this equation. Given the fact that Q is equal to CV, that's the charge on the capacitor is equal to the capacitance times the voltage. Now Q of t is equal to C times what? V of t. Or let's write it as we're going to write it from now on. Q is equal to C E of t, and this here is the voltage on the capacitor. Okay, the amount of voltage on the capacitor. All right, so instead of Q of t, I'm gonna keep this Q of t first of all, but Q0 is equal to what? C E0, right? 1 minus e to minus t over RC. So that's another equation we can think of. All right. Q of t here is equal to C E of t. So that's the what? The voltage on the capacitor is equal to C E0, 1 minus e minus t over RC. And now C with C cancels. So this equation tells us that the voltage on the capacitor as a function of time is equal to this equation. Now after a very, very long time, this becomes 0, just like we have here. After a very long time, this whole thing becomes 0. So the voltage on the capacitor after a very long time at t equals infinity, okay, is actually the voltage of the battery. Okay, that's the voltage of the battery here. So after a very long time, the voltage across the plates of the parallel plate capacitor is equal to the voltage of the battery. What do you think the voltage across the resistor after a very long time? The voltage across the resistor after a very long time is 0. Why? Because current is 0 in the circuit after a very long time. As you can see, this is the amount of charges. If the charge plateaus on the capacitor, what's the current that is flowing through the circuit? After a very long time, I is 0. There is no more charges that are being transferred to the capacitor, so the current dies away. We know that the voltage across the resistor is equal to I times R, and after a very long time, I is 0, then V is 0. Okay, so these are the little things that you need to know about RC circuits. The current is highest at the beginning, then it dies away. and the amount of charge flow into the capacitor is highest at the beginning, then it plateaus, but it becomes a maximum charge on the capacitor. And we also write V now as the electromotive force here. So most of the time we're going to use that one. So the most important equations that you need to learn here is just this one, the amount of charges in the capacitor as a function of time, and these two equations here, and knowing that V is the same as E. And then the rest you can just derive quickly from the other ones. Right, I think it's a good time now to talk about discharging a capacitor. After we talked for a while how to charge a capacitor, let's try and see how to discharge a capacitor. Look, this capacitor here is connected to the battery. So what we do is just take the battery out and then connect the capacitor with the resistor. So what's going to happen is that the charges that were on the capacitor will start feeding into the resistor, so that the current will move this way, and the resistor will have the voltage drop as the charge going into it, and the capacitor will keep discharging because of that. So let's say it starts once we close the circuit like this, once we have the circuit like that at t equals 0, so that's t equals 0 here in seconds, and this is the charge on the capacitor in coulomb, and the maximum charge we said is Q0. Once we have this situation, the capacitor will start discharging quickly, and then it's going to plateau and go to 0 at some point after a very long time. All right, so the equation to discharge the capacitor, Q of t, is actually simpler than the equation of charging it, and that equation is equal to Q0, which is the charge you start with, times e to minus t over the time constant RC. Okay, so this is the equation for discharging the capacitor. And if the capacitor actually, once it's charged, you can make a pattern so that it is not connected to the resistor. Okay, in this case, the capacitor will keep the charge on its plates for a very, very long time, maybe forever if it was well isolated from the world. That's why in the back of your TV they put like some kind of like a lightning arrow, shows you something and says something, risk of electric shock. Even if the TV is not connected to the power and a couple of months pass by and you open the back of the TV because you want to fix it or whatever you want to do, you may still be shocked if you touched the capacitor, the wrong item in your TV, and that's why they make it hard for you to open the back of your TV. All right, I hope this helps. Thank you.